Good morning. In the last lecture, we discussed about Monte Carlo simulation. Basically, Monte Carlo simulation is a method to solve complex problems using method of simulation. Now, when we are using Monte Carlo simulation, one important point is how many samples we should take to solve a problem. Now there are two possibilities. One is we can take a very large number of samples, that is large sample size. But the problem is if I have a large sample size, I have to compensate with long computation time. On the other hand, other possibility is a small sample size. So if I take a small sample size, I can do my calculation fast, but we have to see the accuracy of the result, because in that case I am somehow compromising with the accuracy of the result. So if I take a small sample size, my accuracy of the results suffer. If I take large sample size, I have to pay the price of large computation time. So basically, we need to see something in between. That is, we have to optimize, or we have to look for a solution that gives little bit reasonable accuracy as well as good amount of computation time. So basically both should be relatively less, and we should have a good accurate solution as well as computation time is also small. So this is the idea we will discuss in this class, how we find optimum number of sample size for a given problem using Monte Carlo simulation. So if you see, the sample size in Monte Carlo simulation depends upon two things. First is event of interest. What is the event? Do we require a very high or sophisticated result, very accurate result? That is the event of interest. And the second parameter that decides sample size is the uncertainty or unknown probability associated with the event. If I have a unknown probability is very large, in that case we have to take a relatively large number of sample size. If unknown probability is having a very small interval, in that case we can take a small number of sample size to come with relatively accurate result. Now let us discuss this idea using an illustration. This illustration we also discussed in the previous class. This is about total profit of a company. So a company has some income, it also has some expenses. I can subtract these two, income minus expenses, that will give me the total profit of that company. Let's say R denotes the total profit, I denotes the income, and E denotes the expenses. Now as said in the previous class, these terms R, I, E are basically a stochastic, or we can say these are random variables. So these are random variable, and if you remember, a random variable is generally described by a distribution. So let's say income is described by a normal distribution with mean of 60,000 and a standard deviation of 8,000. Similarly, expenses is described by exponential distribution with parameter lambda that is given 6.25 into 10 to the power minus 5. If you remember, in case of exponential distribution, mean is given as 1 by lambda. So basically lambda is the parameter for exponential distribution. Now these two distributions are illustrated in this figure. So this is the income that is normally distributed with mean of 60,000. So this is income normally distributed with mean of 60,000 and a standard deviation of 8,000. So a standard deviation is 8,000 and mean. So this follows a normal distribution. So income follows a normal distribution. Similarly, we can plot a probability density function for expenses with the given parameter lambda. So this shows the exponential distribution of expenses. Now we can see income and expenses, those are random variables, and correspondingly PDF It's shown in this figure. Now the question is, we have to use Monte Carlo simulation to find probability of loss, that is what is the time and what is the probability that total profit is less than 0. So total profit R is equals to income minus expenses. So we are looking for solution when my total profit is negative, that is we are in the loss. So we have to find probability of R that is less than 0, and then we have to use Monte Carlo simulation method to find solution for this example. So let's take first 10,000 sample and we will use an Excel sheet to illustrate or calculate the probability of loss. So let us use Excel sheet. So this Excel sheet shows income and expenses. So income follows normal distribution with mean of 60,000 and a standard deviation of 8,000. And expenses follow a exponential distribution of lambda 6.25 into 10 to the power minus 5. So we can calculate mean, that is 1 by lambda. So this is the mean for expenses. Now using Monte Carlo simulation, what we have to do first, we have to simulate samples for income and we have to simulate samples for exponential distribution using exponential distribution for expenses. So we have to simulate sample for income as well as expenses. So let us first simulate samples for income, and to do that, let's say we take 10,000 samples. So first column shows you the number of samples, so it starts with 11 and total number of sample we have, that is 10,000, and it ends at cell number 10,010. So if I want to go on the top of this Excel sheet, what I have to do is I have to shift control press at the same time and then press the arrow key, top arrow key. So this will go at the top of the cell. Now let us first generate a uniform random number, and Excel has rand function, so we can use this rand function to generate this random number, and then we can click twice and it will generate all the random numbers up to 10,000. So now I can generate, using this I can generate randomly distributed normally distributed random numbers. So I can write this is equals to norm inverse, and Excel has this function, so norm in and then norm dot in, and then I have to press tab key, and then probability is here, and what is the mean? So mean is this one and a standard deviation is this one. Then I have to press enter key, and let's freeze this two term. So B5, this cell I have to freeze, so let's put $sign before this, and B6 again I can fix this. So this is the normally distributed random number, and if I double click, this will generate all the random numbers up to 10,000. To just check, let us press Ctrl Shift and arrow key down, then you will see all this number has been generated. Now let us discuss for expenses. We have to again generate uniformly distributed random number, and then I can use rand function and then double click, it will generate 10,000 of samples. So in this case I have to drag up to 10,000. So we have simulated 10,000 uniformly distributed random numbers. Now I can go on the top cell and let's find exponentially distributed random numbers. So in the last class we used inverse CDF method to find random number that is exponentially distributed, and for that we have the formula that is xi is equals to ln 1 minus ui, where ui is the uniform random number divided by lambda. So let us use this formula, and there is a negative sign also, so let me put this negative sign. So this formula contains a negative sign. So this will be minus of natural log 1 minus this number, and this divided by lambda. So this value is lambda. Now I can freeze this lambda. So let's say Z6, I have to put this dollar sign. So this gives me the expenses that is exponential distributed. Now I can double click and it will generate all the 10,000 samples. Now I can find the total profit, that is income minus, so this is income minus expenses. So this gives me the total profit. Now I can basically double click and I can get the total profit in each sale. So this is not needed. So now we have this. So basically what we have done, we have generated 10,000 samples of income and expenses as well as total profit. So now we can use this sample to find probability of basically loss, and let us first find or first draw the histograms of these simulated samples. So let us take 20 bin and first find what is the minimum of this data. So this data has up to 10,010, so we can find minimum of that. So this is 10,010. So this starts at cell number I11. So this is ith column and this is 11. So it starts at I11 and ends at last cell, that is I10,010. So this gives me the minimum value. Similarly, I can find maximum value, that is again 10,010. So this gives me the maximum value. We can find what is the total bin interval we want to use for histogram. So this is maximum minus minimum. So bin interval, bin range, that is maximum minus minimum. So this is maximum is N5, this is N6, so maximum is N6. So N6 minus N5, that gives me the bin range. And if I divide this by 20, that is this divided by 20 will give me the bin interval. So now I know each bin size, and we can find what is the lower bin size, or what is the lower bin limit and what is the upper bin limit, and using that we can basically find frequency. So let us first find lower bin and upper bin. So lower bin size, I can say this is the bin interval times this number is iteration number I will have. So this is 1, so first iteration, so A11 is 1, so 1 minus 1, that is 0 times interval, that is 9362 plus lower limit. Lower limit is minimum value, that is N5, so this is N5, that is minus 100596. Now if I want to find upper bin size or upper bin limit, we have to basically take A11. I don't have to subtract 1. So this is minimum plus 1 times bin interval. So this A11 value is nothing but 1 times bin interval. So this will give me the upper bin and lower bin. Now if I drag this will give me bin sizes in other bins also. So I have already done this. If you see, let us check any value. For example, if I want to check this cell, so this is N5 plus A19 minus 1. A19 is 9. So 9 minus 1 into L6. L6 is this value. So this will give me the lower bin and this will give me the upper bin size. In this case, I don't have to subtract 1. So now I know bin size, what is the lower bin limit and what is the upper bin limit. And then I can find how many samples are there in that bin. to find the frequency, that is number of sample in that bin, let us discuss two cases. First case we will discuss, let's take only among the 10,000 sample, we will take only 100 sample. And then in the second case we will take 10,000 all the samples. So let's first discuss 100 sample. If I take only 100 sample, what is the frequency? So we can write this formula, we can use countif function to find how many data we have that lies between in this bin interval. So this function gives me, so this function in the last class also we discussed. This gives me the, so basically countif function requires a criteria range and then criteria. Similarly, if I have two criteria, then second criteria range and the criteria. So first part here, this gives me the criteria range, and the range is nothing but from 11 to 110. So I am taking only 100 sample, and this is the criteria greater than equal to. And I have the second criteria, so greater than equals to K11, and then I have second criteria, so this is my range, that is 11 to 110, so I am taking only 100 samples, and the criteria is this is less than L11. L11 is nothing but upper bin size. So if I use this, I can calculate or I can count total number of sample that lies in this bin, and then I have to divide by 100 to get the frequency. So this will give me the number of samples divided by 100, that will give me the frequency in this bin range. So basically we calculated for all in this case, so you can check any one of the cell, we are using the same formula. I have to take, so this is basically 100, so there is a mistake, I have to freeze this. So this goes, so let's say 11 to 1110, so again I have to freeze this. This means I have to put a dollar sign here, so this is freezed. Similarly here I have to put I11 to I110 only, so this is fixed. So now I can drag this so that I can get, now you can check any cell. So let's, for example, if I check this cell, so this says 11 to 110, and the criteria, this is greater than K21. So what is K21? So K21 is nothing but this and this, so lower limit, the lower bin size. And this criteria is L21, that is upper bin size, and this is I11 to 110. So basically in this case we calculated the frequency for 100 sample, and the same thing we can represent or we can repeat for 10,000 sample. So once again in this case we will use countif function, and we will go from 11 to 10,010. So let us put this, let's put dollar sign here to freeze this. So this dollar, so there is a, so let's put here, so this is, and again here I have to put a dollar sign, and then I can go here and then I have to put a dollar sign and again a dollar sign, and then I have to divide by 10,000. So this will give me the frequency, and then if I basically, and then so this will go to up to 10,010, so 11 to 10,010, and the second situation is again J11 to J10,010. So basically this will not be J, this will be I. So let me shift this here. So now I can shift also, this also goes here. So this is I. So let's check again. So this is formula, this should not contain J, this should contain I, because I am checking in the cell I. So this is for ith cell. We can double click here, and this will give me the priority for our number of samples divided by 10,000. So this will give me the frequency in any bin. So let's try to plot this for 10,000 sample as well as for 100 samples. So I want to plot a histogram for 100 sample. So insert. Now this is for let's say x-axis. For x-axis we can put this lower bins. Basically we should put the the average or median. For example, in this case, let's say for the time being we are fine with the lower bin size. So this will give me for the lower bin histogram. Now in the same graph, let's plot for the, so this is for 100 sample. Let's add one more, and this is for 10,000 samples. Let's call this as a series 2, and in this case value is here. So we can plot this here, and the x-axis is again this lower limit, lower bin sizes. So this one gives me a histogram for 100 sample size as well as 10,000 sample size. So if you see, if you click this, red one is for 10,000 sample size. So if you see, so this red corresponds to 10,000 samples and blue corresponds to 100 sample size. So you see, if you change the number of samples, basically your histogram will also change, and we can see the number of sample size basically changes the distribution of histograms. So if you take like 10,000 and then if you take 20,000, probably if you increase sample size, we may not see so much changes in the basically in this case you can have very similar histogram, but for the time being in this case we have 100 sample and 10,000 sample. We can clearly see there is a change in the histogram. Now let us find probability. First we can find let's take different sample sizes, and we can find what is the sample statistics. So we can take 100 sample, 10,000. So we plotted in this case 100 and 10,000. It is also possible to take different sample sizes. We can take different sample size and we can try to find what is the mean, standard deviation, coefficient of variation, and what is the probability of loss, that is the number of times when we have R that is less than 0. So let us take 100 sample and calculate mean. So we will use for mean, we have formula that is average that Excel gives, and I have the samples here. So I have to take 100 samples. So this goes to I. So this will go here. So I have to take mean of 100 samples. So this will give me the mean. So this is J11 to this is going up to J1 I110. So 100 sample, and then I can calculate what is the mean. Similarly for 100 sample size we can calculate what is the corresponding standard deviation, and the function in Excel is stdev to calculate a standard deviation. And once I know mean and standard deviation, we can basically calculate coefficient of variation, that is sigma divided by mu. So we can find how many, if I take 100 samples only, how many samples that we have a negative, that is R is less than negative. So less than 0 in this case. So once again we will use countif function, and let's say this is my criteria countifs, and the range is I11 to I110, and then I have to check this number is less than 0. So simply I have to put this is less than 0 in this case, because we are interested in. So what is this L34? So let me see L34. Let me put this L34 as 0, or we can simply put here this is equals to 0. So I am looking for a criteria. So this is, so if you see there are only 4 samples that is negative. We can also verify in this case. So let's say one sample is this, that is negative. This is the second sample that is negative, and then we should have third sample, this is negative, and we should have one more sample that is negative. So this is the 4 samples. So in 100 samples, there are only 4 samples that is negative. So we can calculate what is the probability of loss. This divided by number of sample in this case is 100. So we can calculate probability of loss. Now we can basically plot, or we can make a table for different sample sizes. For example, in this case, I have to change this. In this case, I will have 100 sample size. So let's say I have in this case 100 sample size. So this will go from 1000 sample size. So this will go up to 10,011. So this is 11 to 10,011. Similarly, in this case also. So once again, I have to change all this value. So this is 10,011. Sorry, 1,011. So this is 1,011. This is also 1,011, and this will remain same. And coefficient of variation. So this will go from 1,011, and there I have to divide. So we have to divide by so this divided by, so you see in 100 sample there are only 3 negatives. In 1000 there are 31 negatives. And in this case, you see it keeps changing because every time we are generating new random numbers. So similarly, we can fill this for all these cases, 2000, 3000, 4000 up to 10,000. So let me fill this let me repeat this formula for each cell, and then we can plot a graph for number of sample size with let's say probability of loss. So basically I have filled this table, and then I can calculate probability of loss in each case. So you can check any one of the cell. For example, this is mean for data from I11 to 5010. So 500 data in this case we have, and the corresponding probability of loss is here. Now we can see there is a change in a standard deviation as well as coefficient of variation and probability of loss. So we can plot a graph between probability of loss versus number of samples. So let us plot this graph. So probability of loss and versus on the x-axis we will have number of samples. So you see in this case, basically I can plot this graph here. So now if you see in this case, for this particular problem, you can see initially for a 100 sample size, this probability of loss is 0.04. But after this, if I take 1000 sample size, this is 0.22. And then it's little bit same, 0.22, 0.24, 0.26, 0.27. So little bit consistent. So it looks like if I would have taken 4,000 samples or even like minimum if I have taken 10,000 sample, I should have got relatively convergent result. So for this case, if I am only interested in probability of loss, 100 will not be sufficient, but 1000 sample size will be sufficient in this case. Now for example, in this case, if I consider this R is less than 0, but if I consider R is less than minus 20,000, let us consider a different situation. When I am looking for a situation R is less than minus 20,000, in that case probably 10,000 sample, 1,000 sample will not be sufficient, because what I am doing is I am looking for a number in this cell that is less than minus 20,000, and there is very less probability. For example, I have this number, but these all negatives are not less than 20,000. So this means if I am looking for a number that is one side tail of the distribution, in that case I have to take a larger sample size. In that case, it will not be sufficient. It will not be sufficient to take only 1,000 samples. So this we can discuss in this. So this basically be demonstrated using Excel sheet how we can calculate probability of loss. For example, in this case, probability of loss is in this Excel sheet I have 0.275. So probability of loss for a 10,000 sample or even 1,000 sample I have 0.24, but 10,000 sample I have a probability of loss of 0.275. This probability was based on a sample of 275 observation of loss in 10,000 trials. Now, it is expected that a simulation of another 10,000 trial would result in slightly different estimate. Of course, if I take another 10,000 sample, this result will converge or it will result in different estimates, maybe 0.26 or more 0.28, but it should be very close. This is the same graph that we plotted. This is the probability of loss. On x-axis we have sample size. You can see up to this point of time, little bit, let's say this is around 4,000 sample size, the graph becomes convergent, and we should take, if I take a 4,000 sample, this should be sufficient, or even if I can take 100,000 sample, if computation is a problem, in that case, in this case, if I take a 1,000 sample, that will also be suffice. But now let us consider the case of 20,000 as we were discussing. If I am considering a loss of 20,000, so in that case, because this probability is towards the tail of the distribution, so I can see, if you see this distribution, as you remember, we have shown this distribution earlier. So basically income minus expenses. So this means this side of distribution. So this is 20,000 minus 20,000 is towards the tail of the distribution. So there is a less frequency to absorb such kind of event in only 10,000 samples. So in that case, we may have to increase the number of samples. So this means if I'm looking towards one of the tail, then I have to increase the number of sample sizes. For example, in this case, you see, in this case, if I have performed this exercise, only thing is R is not less than 0, R is less than minus 20,000. In this case again, if I take 10,000 sample, and this is the probability of loss versus sample graph. In this case again, you see around 6,000 graph becomes convergent. I can take even more sample size, and then we can see this becomes a little bit same or convergent graph. In that case, we can take 6,000 in this case. If I take minus 40,000, of course, in that case, 10,000 will not be sufficient sample size. We have to take a little bit extra sample size, increase the sample size. So the question is how we require sample size, how we calculate sample size or estimate the sample size. So there is a formula. So this formula says the required sample size can be expressed in terms of coefficient of variation using the binomial distribution, and this is given by this formula where n is the number of sample size, n is equals to 1 divided by coefficient of variation whole square times p when the probability is small. This formula is only applicable when the probability is small. Therefore, for a stopping criteria of coefficient of variation of 10%, so let's say coefficient of variation is 10%, I can plug this is equals to 0.1 whole square. The estimated probability, the number of Monte Carlo simulation needed is 1 by 0.1 whole square divided by p. So this comes out to be 100 divided by p. So therefore, an event of 10 to the power minus 2, that is probability of 0.01, would require 10 to the power 4 simulation for a coefficient of variation of 10%. This means I have a probability of 0.01. This means I need to require 10,000 samples in this case. So depending upon what is my probability, as we were saying in the beginning of the class, what is my probability, sample size will depend upon the probability of desired, and also it will depend upon the coefficient of variation. So coefficient of variation represents the relative variability in terms of estimated probability. So basically we can plot a graph between number of simulation versus coefficient of variation for different values of p. So let us use Excel sheet to investigate more about this formula that says n is equals to 1 divided by coefficient of variation whole square times p. So we can consider different coefficient of variation. So 0.5, 0.4, 0.3, 0.2 and 0. Let's consider probability in each case of 0.01. So we can calculate number of sample size n is equals to 1 divided by coefficient of variation whole square. So this is 1 divided by coefficient of variation is L79 whole square times p. So this will give me the number of simulation required using the formula that we discussed earlier. Let's plot on a logarithmic scale, so we can take log of this number. So log of, and on a base of 10, so log of 400, and that will give me the logarithm. Similarly for 0.4 I can calculate for a probability of 0.01, and this gives me a logarithmic scale. Similarly for this value is not exactly 0, so this is 0.001, so this value is 0.001, and for that case on logarithmic scale we have a value of 8. Now we can plot this for different probability also. So let us calculate the same thing of a probability of 10 to the power minus 3. So this means 0.001, and then we will have everything is same. So this will give me the number of sample size. You see, if I decrease the probability, so this is basically 0.001, number of sample size on a logarithmic scale is increasing. Similarly, I can calculate for 10 to the power minus 4. So this is, now in this case again we have to, now the number of sample size also increases. So now I can plot a graph between, for different coefficient of variation. So let's plot a graph between log n versus coefficient of variation. So we can plot a graph between log n versus, on the x-axis we can plot coefficient of variation. So this is for probability 0.01. So blue line we have for a probability of 0.01, and then we can add another in the same this curve. So let's say I have to select this data, so I can add another series. This is series 2, and the data is here. On the x-axis we should plot coefficient of variation. So this is the graph we should have. So so this will be not this one, this is on the logarithmic scale, so this value. Similarly, I can add another graph, that is series 3, and on the y-axis we will have this value, and then you see basically we can have this graph here. So now see, this one is red one is for 0.001 and this green one is for 0.0001. So that is, so let me check this. So first is 0.01, second is 0.001, and third is basically I should have one less zero here. So this is the graph we can see. So if you see, if you on a logarithmic scale, my sample sizes increases. So if I decrease the probability, so probability is decreasing. So in this case, I have lesser probability, but my number of sample size is increasing, and this increase is plotted here on a logarithmic scale. So you see the important point is my sample size will depend upon desired probability as well as coefficient of variation that somehow represents the uncertainty, that is the probability, the probability of acceptance that is somehow related to that. So this graph is also shown here. So you see for different probabilities, so probability 10 to the power minus 2, 10 to the power minus 3, 10 to the power minus 4. On the x-axis we have coefficient of variation. On the y-axis we have number of samples. So you see, if you increase probability or decrease the probability, and if you increase the coefficient of variation, so if you increase the coefficient of variation and increase the probability, you will have, so let's first discuss coefficient of variation. So if you increase the coefficient of variation, let's for blue curve, number of sample size required will be lesser. If you increase the let's say if you decrease the probability, again you have to increase the number of sample size. So this is obvious from the formula that we gave. So using that formula we can calculate number of sample size. So to summarize, we can say if I am using to find sample size for any Monte Carlo simulation, idea is we have to compromise between accuracy of the result and the computation time. And how to find the optimum number of sample size? So we have a tentative formula that we can use, but the best thing would be we can experiment with different number of samples and we can see when the chain is converging, when we have the same value that is repeating. So upon that we can truncate the chain and we can find number of sample sizes. So we can stop here and we'll discuss in the next class a little bit more about Monte Carlo simulation. Thank you.